Okay, well, hello everybody. Today is May 25th, 2014, and this is going to be a work-through of Riemann's Habilitation Dissertation. You'll find in the video description links to the paper by Riemann, as well as an earlier video a feature video that goes through his paper. As a quick introduction before we start reading through it, and if you make sure you've got a copy, because we're going to be reading the paper itself, and we're going to ask people in the different locations to take part in the reading. In terms of why are we doing this right now, a couple of reasons. One of them is that it came out of the work that we've been doing on the Wednesday economics classes, where we've been going through Mr. LaRouche's book, So You Wish to Learn All About Economics. In Chapter 5, about how technology is produced, Mr. LaRouche talks. Okay. I presume you can hear me. Somebody just muted me. Please don't mute me. In Chapter 5, about how technology is produced, Mr. LaRouche talks about how science occurs and what kind of thinking is required to make that happen. And he talks about 3 levels of thinking that he brings up there: hypothesis, higher hypothesis, and the hypothesis of the higher hypothesis. So a basic hypothesis, according to Mr. LaRouche, is you put forward a thought and you see whether it's consistent with your assumptions. So you begin with axioms, you think to yourself, gee, I wonder if this is the case, and you see whether it's consistent with what you already think. So we do that all the time when we're just sort of playing out ideas in our head if we're not really trying to make a new idea. A higher hypothesis has as its subject those axioms, and a higher hypothesis proves that it says that certain of the axioms that you believe in are wrong and proposes different ones. That's a higher hypothesis. For example, Johannes Kepler, when he creates the vicarious hypothesis in his book, The New Astronomy, and he proves that the assumptions of astronomers who came before him, their mathematical assumptions, had to be wrong, he's opening up the mind to a higher hypothesis, which is his view of the sun being the physical cause for the motions of the planets. So a simple hypothesis is a thought, and you determine whether it's true based on whether it fits with what you already think. A higher hypothesis challenges those assumptions, and if you show that it's right, you've now got a new basis for thinking. As a third level, Mr. LaRouche brings up making hypotheses about the higher hypothesis. Because the authority of science can't lie in its being correct about everything. We've never known everything, although there have been plenty of times that many people thought they had, or at least small numbers of people thought they had, or the people thought that somebody else knew it all, at least. We never know everything, we never will. So the authority for science, you can't say, is it correct about the universe? That's, if it's wrong, obviously it's not very good, but the real authority for science lies in, are we able to make more discoveries? Are we able to progress? That's the test for the real authority of a scientific approach, a scientific method. So I'm going to read a short quote from Chapter 5 of Okay, here's a short quote from Chapter 5 of Mr. LaRouche's book, where he says that, quote, Riemann's 1854 Habilitation Dissertation on the hypotheses which underlie geometry is a hypothesis governing the formation of higher hypotheses for synthetic geometry, and is therefore an explicit statement on the subject of perfecting the hypothesis of the higher hypothesis. And Mr. LaRouche goes on to say that the method developed here by Riemann has been the basis for much of his life's work. So, okay. So this hypothesis of the higher hypothesis is making a hypothesis about higher hypotheses are formed. It means that you're talking about the practice of science, which is higher than the specific thing that Kepler had done in proving that mathematics wouldn't work for the planets and that the physical cause of the sun was needed. And it's certainly higher than a simple hypothesis of you're testing whether you're right based on whether powerful people or commonly assumed ideas are consistent with your thought. Popular opinion is a very simple hypothesis. You're not really thinking about whether those assumptions are true. So that's one reason to be looking at this paper tonight. Another reason is Mr. LaRouche's very emphatic discussion of a shift that occurred in 1900, which he's been bringing up for the past several months. In a paper that he's working on, he said that this shift represented really a turning away from what the Renaissance represented. They're really throwing away the past, half millennium of progress in the concept of science and law is what occurred at this 1900 shift. That shift was a conference, the International Congress of Mathematicians, which, it doesn't sound like a meeting of the, the Bilderbergers or the Illuminati or the Trilateral Commission or something, but this 1900 conference, International Congress of Mathematicians, was very important. At this conference, David Hilbert had put forward some of what he thought were the most important problems in mathematics. And one of those, the one that became one of the, I don't know if I said the most famous, but among the most famous from the period, was whether it was possible to formalize arithmetic. Now you might be thinking, isn't arithmetic already pretty formal? I mean, it's not like you're writing a poetry when you divide numbers. But what he meant by that specifically was taking mathematics and making it not a language about mathematical objects, but to try to turn it into logic. For those of you who don't like math, you'll hate logic. There's about 5 things you can do in logic. It's all about combining statements and ifs and ors and ands and nots, and it's pretty dull. What Hilbert wanted to show was that if arithmetic, adding, subtracting, multiplying, and dividing, if all the laws of arithmetic could be expressed in a logical foundation, then we could say that we're totally confident about arithmetic, that there were no paradoxes lurking in it ready to take down the whole edifice of mathematics and cause David Hilbert to freak out. That'll never happen because it's all based on logic. So Bertrand Russell was ecstatic at the prospect of axiomatizing mathematics. He wrote a book on it, first in English, and then to show he was serious, he wrote a second edition with the title in Latin, so he meant business, called The Principles of Mathematics. And in this book, he goes through a history of mathematics, and then he tries to do what David Hilbert wanted done, which was to make all of mathematics logical. Part of doing that, just very briefly, there's a paper about this in the video description link about Gödel and Russell and the failures of logic. In order to do this, Russell had to exclude self-reference from the language of mathematics. He went to great lengths to do this, and then later Kurt Gödel proved that the whole attempt was impossible, and he found a paradox in what Russell had tried so hard to make paradox-free, meaning that it's impossible to axiomatize mathematics. So, unfortunately, what Kurt Gödel did has not been recognized. Rather, it'd be better to say that what Russell attempted to do has really become dominant in science. Reductionism, empiricism, the idea that science is inducing formulas about observations and that that's really all that you do, which makes it just mathematics with no new principles in it. This is the end of science, and it's wrong. Gödel proved it's wrong. Cousy proved it was wrong several centuries before. Gödel proved it was wrong using Russell's own statements. So, to get to the back to Riemann's paper here, the great importance of what Riemann had done was in pre-answering what happened later in 1900 and showing why it was a faulty thing to attempt. So I think if we have both of those things in mind, the hypothesis of the higher hypothesis, or thinking about the scientific method itself, and if we also keep in mind the evils of the 1900 attempt to destroy science by turning it into mathematics, and then even destroy mathematics, which you might not think of it as being creative, but it's possible to find new things in mathematics, but they won't be fundamentally new if it's all logical. So let's go right ahead. First off, let me, oh, people all muted their video. I was going to ask for a show of hands of who had watched the video, the Habilitation Dissertation video. Did anybody watch that just before this or in the past week or so? Okay, got a couple hands here. Got a thumbs down. We got a bunch of people with their video mutes on. Okay.
Yes.
Okay, good. We got a yes.
I watched the first 30 minutes just now.
Perfect. Good. Good. Okay, well, I'm sort of going to assume that people have watched it, although not entirely. But well, let's get into it, and then we'll go through it. So we're going to read. The way I want to do it is, given the time and the we're definitely going to read sections 1 and 3, and then I'm going to summarize section 2 to make sure that we can get through the whole paper in the amount of time that we have tonight. So, is there anybody who would like to read the introduction, the plan of the investigation? Here or anywhere? Okay. Just the whole thing? Yeah, sure. Here you go.
Okay. Plan of investigation. It is well known that geometry presupposes not only the concept of space, but also the first fundamental notions for constructions in space as given in advance. It gives only nominal definitions for them, while the essential means of determining them appear in the form of axioms. The relation of these presuppositions is left in the dark. One sees neither whether and in how far their connection is necessary, nor a priori whether it is possible. From Euclid to Legendre, to name the most renowned of modern writers on geometry, this darkness has been lifted neither by the mathematicians nor by the philosophers who have labored upon it. The reason of this lay perhaps in the fact that the general concept of multiply connected magnitudes, in which spatial magnitudes are comprehended, has not been elaborated at all. Accordingly, I have proposed to myself, at first, the problem of constructing the concept of a multiply extended magnitude out of general notions of quantity. From this it will result that a multiply extended magnitude is susceptible of various metric relations, and that space, accordingly, constitutes only a particular case of a triply extended magnitude. A necessary sequel of this is that the propositions of geometry are not derivable from general concepts of quantity, but that those properties by which space is distinguished from other conceivable triply extended magnitudes can be gathered only from experience. There arises from this the problem of searching out the simplest facts by which the metric relations of space can be determined, a problem which, in nature of things, is not quite definite. For several systems of simple facts can be stated which would suffice for determining the metric relations of space. The most important for present purposes is that laid down for foundations by Euclid. These facts, like all facts, these facts are, like all facts, not necessary, but of a merely empirical certainty. They are hypotheses. One may therefore inquire into their probability, which is truly very great within the bounds of observation, and therefore decide concerning the admissibility of protracting them outside the limits of observation, not only toward the immeasurably large, but also toward the immeasurably small.
So there is a lot already in that introduction. If you haven't read this paper before, that might have really been a lot, and you might feel like it went over your head. But let's take that apart, because there's a lot already here. Let's take the very first paragraph here. He says that geometry assumes the concept of space. That's probably not shocking. You know, we assume that there's space when we do geometry. And we assume the first fundamental notions for constructions in space as given in advance. So, as an example of that, can anybody think of examples of notions of constructions in space?
What does that mean?
What does that mean?
Yeah, I don't get that.
Yeah, that's the question. What does that mean?
Notions of constructions in space.
Yeah, the notions of constructions in space.
Constructions.
It kind of goes along with the nature of space.
Like the parallel posture and stuff like that?
Yeah, like for example, the existence of parallel lines.
Yeah, that's the notion of construction in space.
Right. It's a notion of space and a notion of a construction in space. So take the example of.
Oh, I was going to say the assumption of particulates as matter, like fundamental particles, etc.
I think most geometers would say that's a physical assumption, as opposed to one about the space in which people think about the particles and the matter doing things. It's very similar, but Riemann's the focus here about geometry. Let's take this example of the parallel lines. So the idea that parallel lines exist. So what makes two lines parallel? You know, if they continue, they'll never meet. I don't think anybody's tried going forever to see if lines ever meet, or what large chalkboard you'd have that would keep going forever. As a matter of fact, that's about the nature of space. It's also about a construction in space. One way of expressing it is that for any line and a point not on that line, an axiom about the construction is that through this point we can make one line that's parallel to the given line. So that's a notion about a construction that we can do in space. Now, here's another assumption about a construction, that we can make a straight line between 2 points. How do we make a straight line? Usually, you just use a ruler. Well, but does anybody have any ideas about how we could define what straight is? How we know if we have a straight line as opposed to a curved one? How do we determine that?
It's not curved.
Not curved. Somebody here says if it's not curved, okay.
It's not other than straight.
If it's not other than straight.
It minimizes the distance.
Say one more time.
Minimizes the distance.
Minimizes the distance. Okay. That sounds pretty good.
Jason.
Uh-huh. Yes.
Oh, we got a question over here.
Well,
Sure.
not a question. Actually,
Or an answer, rather.
An answer.
you can use an X and Y axes to connect the dots and have a point A and a point B, and connect that to have a straight line.
How do you, yeah, that's what I'm wondering. How do you connect them? How do you make sure it's straight? How do you make sure the connection between them is straight?
Oh. I mean, it could be simply as a ruler. It could be measurements mathematically as where on the graph on the x and the y axis you put the line on. That's how you measure it.
Yeah, I mean, I agree. If we already had graph paper and we measured it along it and said, well, is it every time we go right 2, it goes up 1. I guess just the question would then be posed to the graph paper factory of how did they make? No, this is exactly what Riemann's talking about. Is there's an assumption about space that we've got this straight space, and if it's flat, then how do we make this line? But it's still kind of, or maybe I go right 2 and up 1, and then I connect them. How do I make sure it's straight in between?
You got me on that one. I'll have to think about that.
Now look, this is it's kind of it's a funny question. It's a surprisingly difficult question because we don't really think about it as even being a problem that needs to be addressed. Most people don't think about, like, I don't think too many people in geometry class, when you're going to get your compass and you're maybe bisecting an angle and you're thinking how glad you are you're not doing algebra because this is so much more fun. I doubt too many people said, hold on, teacher, how do you know these rulers are straight? It just doesn't really seem like a question anybody would bother asking. But it's an example of the kind of thing that Riemann is looking at. So among these answers, another answer that came from here was holding a rock from a piece of string. So the string would then be straight?
Yeah.
Okay. Yeah, holding a rock with a piece of string, or minimizing the distance between 2 points. So maybe if you had the graph paper and you punched 2 holes in it, and you passed a piece of string through it and then pulled it taut from behind, like you were stitching or something, maybe you'd say, well, that's a straight line because it couldn't get any shorter. So let's sort of leave it a little bit ambiguous right now, but what's not ambiguous is that it's not an illegitimate question. It's actually kind of a tough one. If you take the parallel lines, for example, say, well, if you take 2 parallel lines, let's say we're going to take 2 parallel lines. We're going to go, there's a, we go over to the high school down the street and we go to the football field. And you know what? There's a 70-yard line and an 80-yard line. And this field happens to be oriented, so they're going straight north and south. Those lines seem like they're parallel. What would happen if you really continued those lines forever? Well, even before you went forever, would anything unusual happen if you kept let's say you wanted to make that football field wider and wider and wider, and you just continued those lines out? Would anything unusual take place? Well, if they're both facing due north, those lines are going to meet at the North Pole. Presuming your football field isn't, coming off the surface of the Earth somehow and being held up by who knows what's going to be strong enough to hold this, thing, ramping off the Earth. Right. If you're doing it on the Earth, those 2 lines would seem parallel locally. Globally, on a globe, they are not parallel. They meet at the North Pole. So one of the difficult things about a sphere is that straight lines, let's take that example. Let's use the definition, the proposed definition somebody had said of straight meaning the shortest distance. So, for example, here I've got happen to have a nice space here, and if I, put this piece of string on it, I can pull it taut, and I'd say, well, this purple curve here would be a straight line on this surface, just like a line of, just like one of the lines of longitude on the Earth, one of the meridians. Those are straight lines, in as much as they're shortest. If you just walked without trying to turn, you would keep going on a meridian. It's not true on a circle of latitude, though. If you're very near the North Pole and you walk east, you're not actually going to walk. If you kept going in a straight line, you would not be going on a circle of latitude. Imagine you're like 1 step away. Imagine here's the North Pole, and you're like 10 feet down here, and you're walking due east. you're not going to walk in a circle like this. You're going to end up walking down to the equator. So lines of latitude are not short. They're not shortest lines on a sphere. They're not straight lines on a sphere. If by straight we want to try out this idea of being the shortest. So anyway, so those are some assumptions about space that we make. Now you might say, well, the sphere is curved, but maybe two parallel lines in space could go forever without ever intersecting. Well, if space is flat, yeah. And what Riemann says here, and this is a shocking thing to be saying. This is 1854, so this isn't, Einstein isn't around. In fact, it's because of this that Einstein could do what he did. But he says in the middle of this second paragraph, he says that from this it will result that a multiply extended magnitude is susceptible of various metric relations, and that space, accordingly, constitutes only a particular case of a triply extended magnitude. A necessary sequel, by triply extended magnitude, let's keep going. A necessary sequel of this is that the propositions of geometry are not derivable from general concepts of quantity, but that those properties by which physical space is distinguished from other triply extended magnitudes can be gathered only from experience. That's a shocker. Let's take the Earth. The surface of the Earth is two-dimensional. I mean, there's mountains and it goes up and down, but if you wanted to say where you are on Earth, on the surface of the Earth, all you need to do is say your longitude and your latitude, and you've got your spot on the surface of the Earth. Maybe if that spot is in a building, you might have to say what floor you're on, but if we're just on the surface of the Earth, two things, latitude, longitude, that's all you need, you have a position. It's like on a piece of graph paper. X, Y, that's all you need to say where you are. A piece of paper sure seems to be flat, and the Earth seems to be round, but what they have in common is that those surfaces are both two-dimensional surfaces. Two things that you need to know to determine a position. In contrast, space is three-dimensional. So you could have X and Y and Z. You could have latitude, longitude, and altitude. You could have a lot of other ways of describing a location in space. You could say how far you twist left in your chair, how far up or down you turn your head, and then how many feet away something is. You could use that. Whatever you do, it takes three things to describe where something is in space. And what Riemann is saying is that just as Eratosthenes did an experiment using the sun and shadows to discover that the Earth was certainly not flat, but that it was a sphere, it was round, and to estimate its size, the same thing is true of space. There's a lot of ways to have a three-dimensional volume, manifold. Physical space is one of those possibilities, but which one? Just like the Earth, there's a lot of different surfaces that exist. There's a flat surface, there's a perfectly spherical surface, there's a squished out sphere, there's an ellipsoid. That's leaving aside the mountains and other obvious changes in the surface of the Earth. But which of those shapes is the Earth? And how would we determine it? You're not going to do it by imagining how the Earth might look in your armchair. You might do some of that, but to figure it out, you have to do an experiment. Riemann is saying that space itself could be curved, and we're not going to know what its characteristics are unless we're driven to those conclusions by experiments, not mathematics. So the last thing to point out from this introductory section here, he says at the end, he says the most important systems of simple facts that are laid down, the most important is laid down for foundations by Euclid. That's the most commonly used one. Euclid assumed that space was flat. Riemann writes, these facts are, like all facts, they're not necessary, but of a merely empirical certainty. They are hypotheses. Right? The possibility of having parallel lines a geometer would say that's natural. That's an axiom. Riemann's saying, well, it's a hypothesis. Maybe you're right. Maybe you're not. And so then he says so that you could inquire into their probability. Are they true? Can we look at are things on the very large and on the very small? Is the geometry the same there? We have to find out. We can't just make assumptions, but let's see what we can figure out. So, are there any questions on? I mean, a lot of these concepts are going to come back repeatedly throughout the paper. But if there are any questions about what we just read, feel free to ask them now, or we could, if someone would like to read the next section, that would also be great. Any volunteers? Including here in the studio. You want to? Come on up. Okay, you guys are too slow out there in internet land. Here's Cameron.
Okay. Right here?
Yeah, right, this part.
Okay. The concept of n-fold extended manifold. While I now attempt in the first place to solve the first of these problems, the development of the concept of manifolds multiply extended, I think myself the more entitled to ask considerate judgment inasmuch as I have had little practice in such matters of a philosophical nature, where the difficulty lies more in the concepts than in the construction, and because I have not been able to make use of any preliminary studies whatever aside from some very brief hints which Privy Councillor Gauss has given on the subject in his second essay on biquadratic residues, and in his Jubilee booklet, and some philosophical investigations of Herbart.
I'll say a couple footnotes on that. That's just, you can read the next one too. Just for those who feel like having some sources to look at, the things that he's referring to, those things are the brief hints which Privy Councillor Gauss has given in his second essay on biquadratic residues. That was translated as the metaphysics of complex numbers, and that's in 21st Century Science and Technology magazine. I forget which issue though, but that's where you can find that. When he refers to Gauss's Jubilee booklet, that's Gauss got his PhD in 1799 with a paper that really stunned everybody by showing that the basis of math is geometry, and specifically that the basis of the complex numbers, the square root of -1, I, that it's not just some weird letter that you write with ink on a page and doesn't mean anything more than some magical spell that you do steps to get the right answer and get a good grade, but that there's a geometry to the complex domain. And so that's what he's referring to there. And then I wish I could give something specific on Herbart, but he's a philosopher who had his own ideas of space and on how we would come to discover things about it that Riemann was interested in, and he had read his books when he was in he was at Göttingen University. Those are just those footnotes. Let's go ahead here.
Okay. Notions of quantity are possible only where there exists already a general concept which allows various modes of determination. According as there is or is not found among these modes of determination a continuous transition from one to another, they form a continuous or a discrete manifold. The individual modes are called, in the first case, in the continuous, points, in the latter case, elements of the manifold. Concepts whose modes of determination form a discrete manifold are so numerous that for things arbitrarily given, there can always be found a concept, at least in the more highly developed languages, under which they are comprehended. And mathematicians have been able, therefore, in the doctrine of discrete quantities, to set out without scruple from the postulate that given things are to be considered as all of one kind. On the other hand, there are in common life only such infrequent occasions to form concepts whose modes of determination form a continuous manifold, that of positions of objects of sense and the colors are probably the only simple notions whose modes of determination form a multiply extended manifold.
Let's talk about that. So a couple concepts that came up here. Discrete and continuous. A general concept which allows various modes of determination. And he says that's what quantity is. Quantity is a general concept which allows various modes of determination. Could anybody put that in their own words? Does that make any sense? Does it sound totally cryptic? How do you understand that?
Yeah.
Okay.
Maybe the general, the different modes of determination would be referring to units, perhaps.
Could you give could you give an example?
Like quantity is how much, but then you have to talk about, are you talking about 5 inches or 20 pounds, or what is it you're measuring?
Julia, it's hard to hear you. So if Jason, if you're catching that, can you restate what she's saying?
Yeah, your volume is pretty low there. Juliet said it's like a quantity. She gave a couple. I might be misinterpreting you. If I am, speak up. But she gave a couple of examples, such as 5 inches. She said you need a unit, like 5 inches or 20 pounds. I might take the liberty of saying that that length is a general concept, which you could have specific. Juliet's nodding. Okay, good. Length is a general concept that has specific modes of determination. So there's a lot of different lengths. 5 inches is a length. 10 feet's a length. General concept length. And it has various specific modes of determination. Mode of determination, I mean, this is, I'm sure it sounds much better in German. Mm-hmm. It sounds very awkward in English. If it said various ways of being or various specific magnitudes or something like that, it might be easier to understand. But that's really all that he's saying. If you've got a general concept that could exist in a number of different ways, like the length or the weight. Weight's a general concept, 10 pounds, 20 pounds, 100 tons. So that's what a quantity is. When you got this diversity, that all exists under one concept. So it's not only things that have a common unit to them. It could be something else. It could also be a quantity. Like the people in the room that you're in. That's a general concept, the people in your room, in the room. And there's specific modes of determination. Him, her, this person, that person. So that's another quantity. Now, on continuous and discrete, those are words you may have heard before. Continuous, would anybody like to say what they think the difference is between continuous and discrete? Should I just say anything? I'm worried about that. Okay. Oh. I thought Juliet was reaching to unmute herself. Okay. No? Okay.
Hello?
All right. Well.
Discrete for me is something that, something like start and finish, but continue something that you can't find a start and an end.
Okay. Sounds like it's getting there. There it is. Well, he says what it is. He says Riemann gives a definition. He says, according as there is or is not found among these modes of determination, 2 pounds, 5 pounds, 2 inches, 5 inches, Jack or Julie, whether there is found between them a continuous transition from one to another, then they're either a continuous manifold or a discrete manifold. So maybe if you're talking about the people in the room, using what Fernando said, there's definitely a beginning and an end. Like you're either pointing at Leona or Alicia, and you're not really, there's not a person, an identity of a person in the middle or anything. Yeah. One or the other. Or if you think about, an easy example, a common example is musically the difference between a violin and a guitar. So a violin, you move your finger up the fingerboard, it's continuous. On a guitar, there's frets. So a guitar is discrete. You're on E or you're on F. And you don't really, you can go on, anyway, like a piano, right? The different keys, there's nothing in between two different keys on the piano. So that's an idea of continuous and discrete. And then Riemann had said that among multiply extended magnitudes that are continuous, the only two examples he could come up with were positions of things and colors. Can anybody think of any others? Or is it? Yeah, those are the ones that's all Riemann that's what Riemann came up with. He said, well, in common life there are such infrequent occasions to form concepts whose modes of determination form a continuous manifold that the positions of objects of sense and the colors are probably the only simple notions whose modes of determination form a multiply extended magnitude manifold.
What about speeds?
Okay. What about speed? How do we? Well, I'm thinking also like when he's not really he's about to distinguish between what it means to be 1 or 2 or 3-dimensional. So maybe we should have. Well, say what you mean. In what way is speed a multiply extended manifold?
Oh, I'm sorry. I thought we were talking about a continuous versus discrete still.
We are, but yeah, you're right. Those aren't the only examples of continuous things Riemann could think of. He said those are the only examples of continuous things that have more than one dimension to them. So, speed is more and less, length is more and less, weight is more and less, location is not more and less. We're all in different places on the Earth, but you couldn't say that one of our places is more than the other. That just doesn't really. You might say it's more populated or has a higher elevation or something specific, but just our locations aren't more or less. That doesn't even make any sense. The same thing with colors. So color as let me use this a clip from this video to look at how color gets represented to the human eye.
Hey Jason, what about like a magnetic field? Because that's kind of like a 3-dimensional continuous process.
That's a good point.
Because it has number, has a quantity, and it has space shown.
Well, I don't know. That's a tough thing because it's like it has a value everywhere, but.
But then you could say that temperature, pressure.
Oh yeah, temperature.
Are those all?
Well, but magnetic fields have got, unlike you might measure the temperature everywhere on Earth and say, well, that changes everywhere, but magnitude is more multiply extended because it's got an intensity and a direction.
But isn't light?
That's a good idea.
Isn't light electromagnetic field? So that when you're talking about light as an example of continuous manifold, you're talking about electromagnetic field. It's just that light is what we can see of the total electromagnetic field.
Right, and what Riemann's definitely distinguishing here, he's talking about quantities and measurements and things that we're able to. So, right, there's a distinction between light, what we see, color, which we see. Color is something that's perceived by the eye. Light is different. So we're talking about measuring them, not about what's. When we get to the nature of what's making them, that's something in addition. The quality of light is definitely a multiply extended manifold. Let me just show this. I'm going to show a short clip here from the video on it, so you can see the close-up of. So this is a close-up of what. This is a close-up of a monitor, of a flat-screen monitor, and with a microscope. You can see it's made of red and green and blue lights. So each of the pixels on that display, this is amazing. All this gets fit onto, like a million of these on a cell phone. It's incredible they can make this. So you get all these little lights. So color for the human eye, at least as represented on a television, which isn't the same as light generally, but colors coming off of a computer monitor are three-dimensional. So color on a computer has got an amount of red and green and blue. So it's a three-dimensional magnitude where red and green and blue can all vary independently, and they all come together as one concept of the color that you see. So I think light is another one where, well, I think light's infinitely extended, and we'll get to that. Any other simple concepts that people can think of that are continuous and multiply extended? Also, it could be that multiply extended is unclear.
Yeah.
Why don't we keep reading then, where Riemann says what multiply extended is, and then that might make it easier to think about it.
Okay. Determinate parts of a manifold distinguished by a mark or by a boundary are called quanta. Their comparison as to quantity comes in discrete magnitudes by counting, and continuous magnitudes by measurement. Measuring consists in superposition of the magnitudes to be compared. For measurement, there is requisite some means of carrying forward one magnitude as a measure for the other. In default of this, one can compare two magnitudes only when the one is a part of the other. And even then, one can only decide upon the question of more and less, not upon the question of how many. The investigations which can be set foot about them in this case form a general part of the doctrine of quantity independent of metric determinations, where magnitudes are thought of not as existing independent of position and not as expressible by a unit, but only as regions in a manifold. Such inquiries have become a necessity for several parts of mathematics, namely for the treatment of many-valued analytic functions, and the lack of them is likely a principal reason why the celebrated theorem of Abel and the contributions of Lagrange, Pfaff, and Jacobi to the theory of differential equations have remained so long unfruitful. For the present purpose, it will be sufficient to bring forward conspicuously 2 points out of which this general part of the doctrine of extended magnitudes, wherein nothing further is assumed than what was already contained in the concept of it. The first of these, we will make plain how the notion of a multiply extended manifold came to exist. The second, the reference of the determination of place in a given manifold to determinations of quantity, and the essential mark of an n-fold extension.
Okay. Good. We're not just the stuff about Abel and Lagrange, Pfaff, and Jacobi. That's just we'll have to talk about that some other time. So he still hasn't gotten into it yet. So who could read the section 2 of this part, which goes into constructing increasing the number of dimensions, increasing the degrees of extension here. Oh, sorry, some other answers came in. Sounds. That's a pretty good idea. Sorry, this is from quite the examples of simple concepts that are continuous and multiply extended. Like a sound, you say how loud is it? What pitch is it?
Amber color.
Yeah. Or even just, yeah, you got a violin and you, how loud and what the pitch is. So that's, yeah, Riemann should have thought of that one.
Something on the ear.
Yeah. Now let's not hold him. Let's see. And then another answer came in. Oh. Okay, I'll start watching this. For people who are sending in things via the Google Plus event page, sorry, we'll start looking at that. You could fold a piece of paper, and the fold would connect the 2 points in a straight line. That was an idea about a straight line. And for continuous versus discrete, somebody wrote in a stringed instrument versus a piano key. So, okay, good. Okay, so could somebody read section 2 about how we build up from a one-dimensional manifold to beyond that? I think
I'll be bold in representing our internet friends.
All right.
Be the
Thank you.
guinea pig for this. All right, section 2. In a concept whose various modes of determination form a continuous manifold, if one passes in a definite way from one mode of determination to another, the modes of determination which are traversed constitute a simply extended manifold, and its essential mark is this, that in it a continuous progress is possible from any point only in two directions, forward or backward. If now one forms the thought of this manifold again, passing over it into another entirely different, here again in a definite way, that is, in such a way that every point goes over into a definite point of the other, then will all the modes of determination thus obtained form a doubly extended manifold. In similar procedure, one obtains a triply extended manifold when one represents to oneself that a double extension passes over in a definite way into one entirely different. And it is easy to see how one can prolong this construction indefinitely. If one considers his object of thought as variable instead of regarding the concept as determinable, then this construction can be characterized as a synthesis of a variability of n+1 dimensions out of a variability of n dimensions and a variability of 1 dimension.
Okay. Did that elucidate, clarify the concept for anybody? It's a little bit tough reading this. I guess to try to, well, I think in terms of a simply extended manifold, it was pretty simple. He said that in it, continuous progress is possible in only two directions, forward or backward. So, for example, if the whole world was just a line, or a curved line, it doesn't really matter what shape it's in, because if you're in the line, all you know is you can only go forward and backward. So if everybody lived, like there's a book and then became a movie called Flatland, you could also have a really boring book called Lineland, which is actually described in Flatland, where everybody lives just on a line. Now, if you took that whole line and you bent it or did something with it, nobody in that world would know, because all that they know is there's forward and backward. It doesn't really mean anything what shape the line is in space, because the line is their whole world. So, for length, progress is possible in only two directions. If you've got 5 inches, then any other length is either more or less than 5 inches, or equal to 5 inches. But, you don't, it's not difficult to say more or less. Then he said that if we take our whole manifold and we move it so that every point goes into another point in another manifold, then we're making a second dimension, a doubly extended manifold. One way to conceptualize that, it might be kind of hard, but if you picture it, you take the whole equator of the Earth, and then if you moved it up, you know, an inch north, every location on the equator would correspond to a specific spot on that circle of latitude. And if you moved it, you have to imagine this is continuous, not discrete, because location's not, you know, in inches. You know, and you move it up another inch, another inch, another inch, a meter. Every spot comes to a specific one in the next one. So they're not just totally independent. And that's how you build up a two-dimensional manifold. So if you're a dog, for example, that's what color looks like. Dogs, for them, color's two-dimensional, not they're sort of colorblind compared to us. We have 3 different receptors in our eyes. Dogs only have 2. Anyway, and then so from 2 you could add on, so like every place on the Earth, and then you start adding on altitude to it. That would be a 3rd dimension. So that's actually reasonably straightforward. So maybe we should go ahead to the next part. The language isn't, but the concepts, it's basically that's all there is to it. So could anybody boldly read section 3? Oh, okay. I'm supposed to call on somebody, I hear. All right. Could somebody from the Einstein group in Leesburg please read section 3? You are muted. Hey, Leesburg, you unmuted? Okay, now you're good.
Now I'm good?
Yep, go for it.
Oh, okay. All right. So I have a different translation.
That's okay.
I have the one that's murkier, even murkier than what you guys are doing.
All right, well, it'll be a fun challenge. Go for it.
All right. So number 3, let's see. I shall show how, conversely, one may resolve a variability whose domain is given into a variability of one dimension and a variability of fewer dimensions. Okay. To this end, let us suppose a variable piece of a manifold of one dimension, reckoned from a fixed origin, that the values of it may be comparable with one another, which has for every point of the given manifold a definite value, varying continuously with the point. Or in other words, let us take a continuous function of position within the given manifold, which, moreover, is not constant throughout any part of that manifold. Every system of points where the function has a constant value forms then a continuous manifold of fewer dimensions than the given one. These manifolds pass over continuously into one another as the function changes. We may therefore assume that out of one of them, the others emanate. And speaking generally, this may occur in such a way that each point passes over into a definite point of the other. The cases of exception, the study of which is important, may here be left unconsidered. Hereby, the determination of position in the given manifold is reduced to a determination of quantity and to a determination of position in a manifold of less dimensions. It is now easy to show that this manifold has n-1 dimensions when the given manifold is n-ply extended. By repeating then this operation n times, the determination of position in an n-ply extended manifold is reduced to n determinations of quantity. And therefore, the determination of position in a given manifold is reduced to a finite number of determinations of quantity when this is possible. There are manifolds in which the determinations of position requires not a finite number, but either an endless series or a continuous manifold of determinations of quantity. Such manifolds are, for example, the possible determinations of a function for a given region, the possible shapes of a solid figure, etc.
Okay. So yeah, that's that. Anybody?
It's hard
kind
to
of.
understand what he's saying.
It's kind of hard to understand what he's
Without an
saying.
example,
Yeah.
yeah. It's
Well, you know what? I'm almost thinking it's really not even that important to understand the way he's saying this one. So that if you have a multiply extended manifold, if you've got, start with one concept that you want to measure to pull apart from it, and then when you pull that out, you'll be left with a manifold of one less dimension. So, for example, for a location in space that's triply extended, what those triple extensions are, you don't really know. Like, it's no more true to say that every location in space is latitude, longitude, and altitude than it is to say that it's x, y, z, or to say that the location of your coordinate origin should be the sun versus the earth. It just sort of doesn't really matter. Or you could use cylindrical coordinates or spherical coordinates or weird other coordinates if you wanted. It just doesn't matter. But once you pick one thing, for example, if I started by saying everything has a distance from me, that's this function that he says that we could imagine. So everything has a distance from me. If I said everything that's 4 feet from me, I've just created a sphere, and that's a doubly extended manifold. So space was 3. My one concept, distance from me, is a single extension. And then by picking that, everything that fits that condition has got one less amount of variability in it. So you could say everything that's 3 feet off the ground, that's the surface above the earth. It's two-dimensional. Everything that's 10 feet underground, that's a two-dimensional surface. So location, which is 3 dimensions, although not a specific 3, you start making it have specific dimensions once you start choosing what things you're going to measure about it. This might be a way of saying what he's doing there. At the end, he said that there are some things where when you measure them, you can keep taking away, you can keep measuring one specific thing about it, and then measure another thing about it, and then measure another thing about it, and another thing about it, and it's possible that you'll never end. For example, if I said everything that is 2 feet off the ground, and everything that is at this latitude, and then everything that's at this longitude, I've just got 1 point now. There's no more uncertainty about where I am. Or if I said here's my coordinate axes right here, and I said everything that's got 3 inches of x, I got a plane. And then I say everything that's got 4 inches of z, and I cut my plane. I've got a line now. Everything on this line of this arm here is 3 inches in the x direction, 4 inches in the z direction. But now along the y direction, once I pick where along the y direction, I've got a point, and I'm done. I can't. That's it. Space is 3-dimensional. It took me 3 things, and then I said something specific. Riemann says that there are some manifolds that do not have a finite number of dimensions. Now, that's a tough one. So he gives a couple examples of that, like all all functions, all shapes of a figure in space. Those are the sort of things where everything, well, how many sides does it have? But it might not be something that has sides. Or, what function is it? Does it have an x in it? Like if you're playing like 20 questions or something, you'd have to ask an infinite number to be able to. If all the answers could be like not you're thinking of somebody or the color blue or a folding desk chair or something. If you're thinking about a function, people might have to ask you an infinite number of questions to find out. It doesn't sound like a very fun game to play on a long car trip. Another example of it, a specific example I'll show you is light. This is a clip from the video also. So this is a chart so this is for light filters, you know, for like in a studio to put in front of the lights. And what you got here is you got these numbers here. That's the wavelengths of light in nanometers. And then you got this number here. It's a percentage from 0 to 100%. So for every wavelength of light, if you broke it out with a prism into its spectrum, this particular cyan filter allows, you know, at 460 nanometers, it lets 78% of the light through. Down here at 660 nanometers, it only lets 48% of the light through. How many filters could there be? How many dimensions are there? Let's say we're gonna take all of our light, all of these filters, and we're gonna stack them, and we're gonna put them in some sort of filing cabinet. Now, all the colors on the monitor, the TV, they got a red coordinate, a green coordinate, and a blue coordinate. So you can imagine a color cube, where your location in that cube would tell you a color that your monitor could have displayed. Just like the X and Y and Z, you'd have the red and the green and the blue. The space of a monitor, of color space on a computer monitor, or for the eye, since we have 3 receptor color receptor cells, is 3-dimensional. If I wanted to put these things in a filing system, it actually has an infinite number of dimensions. Because I could say, okay, how much light does it let through at 420 nanometers? How much light does it let through at 421 nanometers? How about 422 nanometers? How about 423 nanometers? And then how about at 421.1 nanometers? So there's an infinite number of questions that you could ask. So light filters are have an infinite number of modes of determination. Light itself has an infinite number of modes of determination, even though when we see it, color perceived by our eyes, 3-dimensional. Light is infinitely dimensional. So, like, here's an example. I'll show you how as this curve changes, there's a whole shape to this curve, but it just turns into one color. And all the possibilities of the shape of that curve, when they turn into one 3-dimensional color, you know, you lose something. Okay, so anyway, so there's an example of something that's got an infinite number of modes of determination. So now we're at section.
Can I ask a question
go ahead.
about that?
Sure.
I'm trying to grab onto.
Could you? It's kind of not that loud. Could you speak up, or I'll just repeat it if it's too quiet for people. But.
Okay. Can you go through that again, because the modes of determination, I can't quite think about what. I can see that the types of color, I guess. Well, could you just say it again, how it's infinite, because it wasn't really clear.
Yeah, sure. It's a good question. This is a tough one. If I was placing an order for a certain kind of shoe, you know, I'd say my model number for the shoe, and I'd say what shoe size I've got. So, you know, would it be 8 or 9 or 10 or 11, you know, whatever. There's one number that you put in for the size of the shoe. Let's not worry about wide shoes. Now, if you're ordering pants, there's 2 numbers, right? If you're saying you wanted to specify a specific color that a computer monitor could display, there's 3 things that you would have to say to specify: the red and the green and the blue. Or there's other ways of specifying color, like hue, saturation, and value. There's lab, LAB. So there's anyway, but they got 3 things, because fundamentally this is what's going on in the computer monitor. How bright is the red and the blue and the green? So you can specify any of these colors that a monitor can display with those 3 things. It's not the same as trying to say what kind of light something is. For example, if you mix red and yellow light, it looks orange. Your eye can't tell the difference between orange light that went through, you know, like if let's say you had a prism and you pulled all the colors of the rainbow, and then you took the red and the yellow and you put them back together, and you know it would look orange. Let's say you took a prism and you only let the orange light through. Your eye can't tell the difference. They both look orange. But if you had a prism, you could split one of the oranges back into red and yellow, and the other one would just be orange. So there's much more to light than we can see. Colors that look the same to us could be distinguished by a bird, for example, because birds have got 4 different color receptors. If birds made computers, then their screens wouldn't be red and green and blue. They'd be red and yellow and green and blue. And when they're doing Photoshop or whatever, they'd have red and yellow and green and blue to pick their colors. You know, if they wanted to Home Depot to get some paint matched, they'd be very picky customers because they can just see more. There's just more that they can see in light than we can. So for light itself, basically, let me show this color curve again, the spectrum here. Right. So see if, I don't know if this works, Juliet. So this is the perceived color as it would display on a monitor that would look like, in other words, if you bought a gel filter that looked like this and you had sunlight going through it and it let a lot of the green but not much of the purple or the red through, it would look like this to you, a vaguely bluish color. But if I wanted to say exactly what this filter is, I don't have to just say red and green and blue. I've got to say how much of this color purple does it let through? How much of this color purple does it let through? How much of this blue? How much of this green? Go back. How much of that color purple? How much orange does it let through? How much yellow does it let through? I'm never going to be done. It'll really take me forever. If I'm, the salesman and I'm taking an order, and you just ordered some shoes, and you ordered some pants, and then you ordered a color that could be made on a computer monitor, and then you're ordering a gel filter like this, I'm going to be filling out the form forever because every different wavelength of light, you could say, do you want between 0 and 100% of that light to go through? So it's an infinitely, it'll take you forever. It's infinitely dimensional, light itself. Even though our eyes, we can't see that, but that's because of the physiology of our eyes. There's nothing inherently three-dimensional about light. Birds, they would see it as 4-dimensional. Dogs would say it's 2-dimensional. So it's just because we're human beings and we've got eyes and we developed on the planet Earth. Could be sentient life somewhere else in the universe, and it uses 4-color monitors. So anyway, so does that make it clear why? Does that work?
Yeah, because the spectrum of light is continuous, right? That's what causes that to happen.
Exactly. Right. Yeah. The spectrum of light is continuous. If you if light could only, if you could only go like every nanometer, like 420 nanometers and then 421, and you could say how transparent the thing was, yeah, then you could just go every, then it would be like a few hundred, but you could say it. But the fact is that every individual wavelength along there, it's continuous. So you're never going to be able to finish counting up how many, the number of different colors of light in the spectrum is infinite.
Can you have a discrete, can you have something that's discrete with an infinite number of determinations?
Question here is, can you have something discrete that has an infinite number of determinations? You mean a discrete manifold that's infinitely dimensional?
Well, isn't light just a continuous manifold? Isn't that why it has an infinite number of determinations?
Well,
sorry, those determinations are infinite. It's that one determination that is infinite.
Right. The number of determinations is infinite. Wavelength, or hue, or color angle, or whatever you want to call it, where you are on the spectrum, frequency, that's continuous and singly extended. For every color on the spectrum, you can either say, oh, in this direction or that direction. It's just that to specify the kind of light filter that you want to order,
yeah,
each of these infinite things has its own transparency. So.
Okay.
I would say it's fortunate that our minds are infinite. Otherwise, we wouldn't have such wonderful colors as burgundy and mauve.
Isn't that wonderful? Okay. So that might mean it's time to go to the next section. Anyway, yes. Oh, and just one last thing about light that's interesting is that there's some colors that don't exist on the spectrum anywhere. namely magenta. You know, light doesn't curve around from red to purple and go through magenta. The eye does. Birds, you know, red and purple are not actually similar colors, but they seem like they're right next to each other to us. That's also something about the physiology of our eyes and our vision. It's not about red and purple light don't have anything to do with each other any more than red and green light do. I mean, let's say that this color receptor, you know, didn't see any of this. Like we can't see ultraviolet. Let's say our vision ended right here at cyan. What we call cyan and red would look very similar. So it's all just part of what your brain's doing, and you know, I mean, in fact, what we're experiencing in our minds right now, what I see as red, it's not. You might see it actually differently. You really don't know what's going on inside someone's mind. Anyway, it's true.
Jason?
Yes.
When we're talking about being able to count in a discrete manifold, that's infinite. To try to imagine something like that, I think is different, and I think Riemann talks about this later. That's a different idea than trying to count something in a discrete manifold that goes into the infinitesimally small. And he makes that distinction later. I mean, if you were to imagine the universe going out into infinity, you might be able to imagine counting, say, the number of stars or mass, you know, whatever you want to call it, you know, mass particles or whatever out there, going into infinity. You might be able to imagine that. But when you're going into the infinitesimal, on the small scale, going into the smaller, you can't even imagine that in terms of a continuous, or, you know, trying to figure out what a discrete manifold would look like going into the infinitesimal.
You're right. A discrete manifold in the infinitesimal doesn't really make much sense.
It's a contradiction, yeah.
Yeah. Yeah, and we'll get to that at the application section. Let's move it.
I just thought maybe that was what Julia was getting at, maybe or maybe not.
Okay. So the second section here, just you know. So here's the summary of part 2, so that we can. I mean, you know what? We can set up another time to go through it in more detail later. But in part 2, Riemann goes through a lot of the things that Gauss had done in looking at general surfaces to apply that concept to space. So let me give a few examples of let me just go through this checklist here. Yep. Okay, good. So if you want to measure how curved a surface is using the method of Gauss, let me show a video of that. Here we go. So here you can see a couple of different curved surfaces. Actually, now it's out of focus. There we go. So I guess if I'm back here, it'll help. So here you got a sphere, and here you got a hyperbolic paraboloid, or you could call it a monkey saddle. They're different shapes. How do we start to quantify and measure and understand how they're differently curved? These are both two-dimensional things. If you were a flat creature and you lived on them, you'd say, my home is two-dimensional, and because it is. So the first method that Gauss had used was to, here we go. I'm watching the video together. Normals. So a normal is something that sticks out perpendicularly from a surface. So here you're seeing a normal moving along this monkey saddle, and that blue line is always sticking straight up out of it. This is from the video in the video description. So now what we're doing is we're using, Gauss calls this an auxiliary sphere. So this is a helper sphere as a way of representing direction in space. So whichever direction this normal is pointing, it's pointing the same way on the sphere, and it's sticking normally out of the sphere. So every location on this shape has a location on the sphere, the location isn't related to the location. It's related to which direction the normal is pointing. So we can watch that move around a little bit. And you can see that sometimes they move in the same direction, sometimes they don't. Right, so they're moving in opposite directions now, or partly the same. Anyway, so this is a tool that Gauss had used to measure curvature. So, say about this. Yeah, it's like having a compass, which tells you direction in 2 dimensions. Bruce Director looks very much like Carl Gauss. Okay, and so here we've got two shapes being drawn on this surface. This is called a catenoid. Oh, it's disappearing already. Well, you saw them. There were 2 shapes on this catenoid, and they were similarly sized regions. And you can see that the shape that the normal traces out on the auxiliary sphere is different. So let's take a look at another example here. Here we go. So on this monkey saddle, if we contrast this region and this region, we're cutting off similar sizes, similar amounts of area on those 2 portions. Right? These 2 circles are about the same size on the monkey saddle. If you look at what they turn into on the auxiliary sphere, the red circle is much larger than the blue one, which is very small, and hopefully you can see this. If you can't, you can watch it in the video later. So Gauss would say that this means that the red part of the surface is more curved, because the normal has changed more. And the blue part is flatter, because the normal has changed less. We're putting these flat objects in 3-dimensional space, and yes, we are assuming the space is flat. We are doing that right now, but we're going to go beyond it. So, okay, and one more example. Here's a cylinder. Maybe you didn't know this, but a cylinder is flat. We're going to mark off this large area on the cylinder, and the corresponding area on the auxiliary sphere is just a line. It has no area. The area is 0. So how curved is this? 0. And you can take a flat piece of paper and bend it into a cylinder. It's the same shape, really. If you lived on a flat piece of paper and your world turned into a cylinder, you're not going to notice. You certainly can't bend a piece of paper into a sphere. Not without crinkling it up or bending. You know, you can't do that. So, okay. So that's one of the techniques here. Let's see. This is a question that just came in. Okay. So that's one technique. Oh, and here's the next technique. Osculating circles. So hopefully you can see this. There's a green plane that's now cutting through the monkey saddle, and this green line marks the intersection. If I rotate the plane, I'm getting a new curved line of the intersection. Now I've got this large circle here. Every curve looks like a circle right at one spot of the curve. And this is called an osculating circle that fits it very well. Osculating means kissing. So this circle is just the right size to give it a smooch. As we turn it around here, now you can see this is the size of circle that really well matches the green curve here. So another technique that Gauss gives for measuring how curved something is to use 2 special osculating circles. He proves that for any spot on a surface, the 2 most opposite osculating circles are on perpendicular planes. Let me explain that, okay? That might be tough. So let's use this thing we got here. Now, hopefully that works okay. So like if we take this spot right here. just to mark this. Okay. Here's our red spot. If I cut it in this direction, oh, maybe you can see that. I hope you can. You know, I could put I would say, well, this is the size of a circle that fits along it in that direction. You can see how big this circle is, what its radius is. If I then could go about 45 degrees, you can see what shape this would be. It's a larger circle. It's flatter in this direction. And then from this angle, right at that spot, that's as flat as you're going to get it. It's a much bigger circle. So the biggest circle, and then as we twist, we get to the smallest circle. And the directions of those circles were perpendicular. In other words, the smallest circle was on the cut that was in this direction. And the largest circle was in this direction. And please have fun with this. Play with this with any object you can find. This is always true. The most divergent circles are always perpendicular to each other. Let's take a look at another spot. Right here in this lip area. Right here, this spot. So now the two circles are very, very different. In this direction, I've got this circle, small. Its center is inside the vase. But if I went in this direction, the up-down direction, the circle actually fits outside of it. It looks like about, yeah, it's very small. You know, a smaller circle like this would fit it well there. So in this case, we got a small circle. They get bigger and bigger and bigger. And then we have a small circle that faces in the opposite direction. When the two osculating circles are on opposite sides of the surface, it has negative curvature. That's the definition of negative curvature. So Gauss, the area, if you had that normal and you compared the area on the surface and the area on the sphere, a more curved surface has more area on the sphere with the normal. That's one measure of curvature. The osculating circles, if you measure the radius of both of them, and multiply it, that gives you a measure of curvature. So those are examples of, this is not like a comprehensive guide of measuring curvature, but that gives you a couple of ideas. They both use the shape of the surface in space. And let me show you, this is an example of a very famous discovery based on, okay, we saw that. Yep, we're going to look at Eratosthenes, who, he made a discovery. So here's Eratosthenes, you know, he's in Egypt here. And he's noticing that on the day of the spring equinox, the summer solstice, there's no shadow here in Aswan, and here in Alexandria, the same day of the year, there is a shadow. So he figures out that, well, the light from the sun's coming in all parallel. If there's no shadow here and there is a shadow here, based on the angle of the shadow, the distance between the points, he calculates the size of the whole Earth. It's 250,000 stadia, whatever that unit is. Apparently, experts say this is a very good estimate. So that's what he did. Now, but how would Eratosthenes have done that if he couldn't look out? If he wasn't able to use the sun, which is outside the Earth, just like we were using space outside of those surfaces? How could you do it only inside the surface? That's a tough question. So here's how he could have done it. Yeah, here we go. So here's Eratosthenes. He's measuring the shadow. But if the... No. But if it was cloudy all the time,
Yeah.
if it was always cloudy on the Earth, Eratosthenes could not have figured out the size of the Earth. He needed the sun outside the Earth. Is there any way without going off the Earth, or without using a... kind of embarrassing. Is there any way without using something outside of the Earth that you could determine its size? Let's take a look. So, okay. So here we are in flatland. So we've got different polygons. They all live in flatland on this, you know, I guess she doesn't want to talk to them. They all live on this, you know, graph paper world, and it seems like it's flat. Well, it's definitely two-dimensional. Our friend, it's definitely two-dimensional, but it might not be a flatland. It might be sphere land. How would the people in this world know that? How would these people know whether it was flat or not? Well, there's oh. I like that back. Okay, so how would the people in flatland, in surface land, how do they know if they live in flatland or not? Maybe they think the book was mistitled and it should have been called Sphereland, not Flatland. How are they going to figure it out if, unlike Eratosthenes, they can't look at the sun because they can't look out? They're flat. There's a couple of ways they could do it. One of them is that, I meant to bring this up earlier, there's an idea that all triangles have 180 degrees in them. Why don't I just show the example? Uh-oh. There we go. Here's a proof that shows that in a flat world, the sum of the angles in a triangle are 180. If that didn't make sense, don't worry, obviously it was 5 seconds long. Here's some parallel lines. Okay, there we go. So here's a triangle on a sphere. The sum of its angles is not 180. What are the sum of the angles here? 90, 90, 90, 270, not 180. So that's one thing that the flatland people could do. The polygon, you know, the pentagons and circles and squares, they could measure out triangles and say, wait a minute, the angles in this triangle are 270. Whoa, what's going on? They'd have to measure a big triangle. You know, they have to like go on an expedition, something like that. And the same thing is true on the Earth. If you do surveying, you find out that that's how you can figure out the shape of the Earth without going off of it with a satellite like NASA does. You do it by doing surveying points along the Earth and finding out the angles and you put the whole thing together. So that's one way of doing it. Another way is the Pythagorean theorem, which the Pythagorean theorem is about squares that touch each other and then make a triangle in between them with the right angle. If you put squares on each side of this triangle, let's say this is A and B and C, you've heard that A squared plus B squared equals C squared. Here A squared is B squared is C squared. So the Pythagorean theorem is not true either. So intrinsic geometry, where you're in the surface and you're able to figure out what its shape is without using the space in which it exists, the normals required a shape in space. A piece of paper and a cylinder are completely equivalent, according to Gauss and Riemann. As long as you bend something without tearing it or stretching it, you didn't change the surface. Everything that's true on a flat plane is true on a cylinder. In terms of short lines, how the Pythagorean theorem works, the angles in a triangle, no changes. So that's what Eratosthenes could do, even if it was always cloudy. We can use intrinsic measures. Now, that's what we need to do ourselves because, you know, we're in space, right? We can't go into the fourth dimension and look down on the space that we live in and see how curved it is. We're in it. So we can't do what Eratosthenes did and use the hint of something outside the surface of the Earth. We are like the flatland people in space, in as much as we've got to figure out how space is operating, but we can't go outside it. It's also... What's that?
At least our senses are stuck in that.
Yeah. 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 I mean, we don't, without using a fourth spatial dimension, we can still conceive of it as being curved.
Yeah.
Like the flatlanders, even if they're never able to imagine 3 dimensions, what would they think a sphere is like?
Yeah.
What would that mean to them?
Right.
You know, because it's really tough for us. Like people, you know, you can study Einstein's general theory of relativity, and you can try to think of a curved space, but you're probably thinking of curved things in space. It's really hard to think about space itself not being flat. It's very challenging, and you have to be thinking about it in terms of what things do as opposed to shapes. Is really the only way to get it. That's what the flatland people would have to do. So. Okay, so that's my summary of part 2. So basically, in this whole section here, Riemann takes what Gauss had done with surfaces and talks about how you would do it with spaces. So let's go ahead and pick up and read section. Let's make sure we get. Let's read through section 3 now, and then if there's specific questions about this, we can talk about it at the end. About those ways of measuring things. So maybe somebody in Houston could yell the first section. You want to give it a shot, Juliet? Let's see if we can hear her.
This is number 3 of section 1?
Number 1 of section 3, application to space.
Okay, sorry.
Can you guys hear her okay?
Yeah. Oh, can you hear me? Let's see if you, is this okay? Can you guys hear me?
There's no complaints, you're good.
Okay. So tell me if I'm in the wrong spot, but I'm starting at the very beginning of number 2, the title.
Number 3, application to space.
I'm sorry. Okay. Applications to space. 1. By means of these inquiries into the determination of the measure relations of an n-fold extension, the conditions may be declared which are necessary and sufficient to determine the metric properties of space, if we assume the independence of line length from position and expressibility of the line element as the square root of a quadratic differential, that is to say, flatness in the smallest parts. First, they may be expressed thus, that the curvature at each point is 0 in 3 surface directions, and thence the metric properties of space are determined if the sum of the angles of a triangle is always equal to 2 right angles. Secondly, if we assume with Euclid not merely an existence of lines independent of position, but of bodies also, it follows that the curvature is everywhere constant. And then the sum of the angles is determined in all triangles when it is known in one. Thirdly, one might, instead of taking the length of lines to be independent of position and direction, assume also an independence of their length and direction from position. According to this conception, changes or differences of position are complex magnitudes expressible in 3 independent units.
Tough. Okay. We got these. So we got three possible ways that space might be. The Riemann's looking at. So the first, maybe it's flat. Oh, sorry. Measures of curvature. A surface has one measure of curvature at every point. You could say its curvature is 0 if it's flat. here the curvature would be a negative number, like -10 or something. Here it would be, it's positively curved, but it's not, it's reasonably flat, so maybe it would be like 3. In space, every location has 3 measures of curvature because there are, anyway, that's how it works in space. So he's saying first case, space is flat. All triangles have a sum of 180 degrees. Maybe that's how it is. Okay. Second, this is interesting. He's being polemical here with describing this to Euclid, I think. He's saying, secondly, let's assume, like Euclid, that bodies don't change when you move their locations. So, for example, the example in the video is an orange. If you take off a piece of an orange peel, it fits anywhere on the orange just fine. It's not true with a watermelon, where it's flatter here and it's more pointed at the ends, or a pear, which has got a pointed end and a more flat end. So, if he says, like, if we assume, like Euclid, that bodies don't, that all locations are equal to each other, that would mean that it's more like, on a surface, a sphere, where the curvature is constant everywhere. So that's the second case that Riemann gives. The measure of curvature is constant. Once you measure the angles in one triangle, then you know the sum of the angles in any other triangle. And then in the third case, that's just everything's open. In the third case, space isn't flat, and it's not constantly curved, and who knows? So those are our possibilities. So let's go ahead and read part 2. Any volunteers? Okay, Wes, come on down.
Okay, can I be heard?
Yep, go ahead.
In the course of the preceding discussions, in the first place, relations of extension, or of the domain, were distinguished from those of measurement. And it was found that different relations of measures were... Are there complaints?
No, go right ahead. That was just a little glitch.
Okay. Oh, okay. Sorry, in the course of the preceding discussions, in the first place, relations of extension, or of the domain, were distinguished from those of measurement. And it was found that different relations of measure were conceivable along identical relation of extension. Then were sought systems of simple determinations of measure by means of which the metric relations of space are completely determined, and of which all theorems about such relations are a necessary consequence. It remains now to examine the question how, in what degree, and to what extent these assumptions are guaranteed by experience. In this connection, there subsists an essential difference between mere relations of extension and those of measurement. In the former, where the possible cases form a discrete manifold, the declarations of experience are indeed never quite sure, but they are not lacking in exactness. While in the latter, where possible cases form a continuum, every determination based on experience remains always inexact, be the probability that it is nearly correct ever so great. This antithesis becomes important when these empirical determinations are extended beyond the limits of observation into the immeasurably great and the immeasurably small. For the second kind of relations obviously might become ever more inexact beyond the bounds of observation, but not so the first kind. You want me to keep reading? Yeah. Well, When constructions in space are extended into the immeasurably great, unlimitedness must be distinguished from infiniteness. The one belongs to relations of extension, the other to those of measure. That space is an unlimited, triply extended manifold is an assumption applied in every conception of the external. By it, at every moment, the domain of real perceptions is supplemented, and the possible locations of an object that is sought for are constructed. And in these applications, the assumption is continually being verified. The unlimitedness of space has therefore a greater certainty, empirically, than any experience of the external. From this, however, follows in no wise its infiniteness, but on the contrary, space would necessarily be finite if one that bodies are independent of the situation, and so ascribes to space a constant measure of curvature, provided this measure of curvature had any positive value, however small. If one were to prolong the elements of direction that lie in any element of surface into shortest lines, or geodetics, one would obtain an unlimited surface with constant positive measure of curvature. Consequently, a surface which would take on a triply extended manifold, the form of a spherical surface, and would therefore be finite.
Right, that would be that second case that he had said in part 1. So let's so a couple things came up here: measure versus extension, unlimitedness versus infiniteness. Did anybody get an insight about the measure versus extension and unlimitedness and infiniteness? He says that space is, he says the unlimitedness of space is more certain than anything we've experienced. Space is undoubtedly unlimited. But its infiniteness does not follow from that. Can anybody explain why that is in their own words?
Because you don't know the shape of the space. If you're a flatland person on a huge sphere and you're a little speck, you don't know that there's a boundedness to the sphere, that it actually has a boundedness to it.
Now, that's, could you guys hear that on the internet? Yes, okay, good. Yeah, so think about that word. That's a really good point. Think about the word boundedness there, because boundedness could have kind of both meanings. It could mean unlimited, it could mean the sphere is not infinite, but think about the different kinds of boundaries there are. Is the sphere infinitely large? No, it has a finite size. Is there a boundary like a fence that you can't cross? No, it's in that way it's not bounded. So it's, you know, that's the unlimited versus infinite thing. The flatland people, they're walking around, they don't ever hit a wall, but that still doesn't mean that they live in an infinite world. So the same with us. Riemann's saying just because we've never seen anything remotely like a wall at the end of space, whatever that would even mean. Like, you know, you start walking and then you know, like a dog running into a glass door or something, or a bird. That doesn't mean that space is infinite. Then he said the same thing again, that if bodies are independent of situation, meaning that if the curvature is constant, then it might, if it was even the littlest bit positive, then all of space would be finite. Wow. Imagine that. So, and then let's read this third section. Any volunteer for section 3? Oh, sorry. Measure and extension. Right, yeah, sorry. Measure and extension go hand in hand with limitedness and infiniteness. If something's unlimited, then you can't, there's no limit to your extension. So unlimitedness applies to extension. Infiniteness, meaning that its actual size is infinite, that would go along with measure. So if the surface land people lived on a huge sphere, their extension would have no bounds. Their extension would have no limits. It would be unlimited. But their measurement would not be infinite. They could measure, we talked about how, with the Pythagorean theorem or with triangle angles, they could definitely measure that world that they live in, and they would know it was finite. They could measure the total surface area of their universe, for example. But still, any extension that they made would be unlimited, because you could just keep going and around and around and around. So, yeah, a good distinction. Part 3. How about somebody from Virginia, from Percival? Huh? You up for it? Okay, you can read this one if you want on paper.
Section 3.
Mm-hmm.
Questions concerning the immeasurably large are, for the explanation of nature, useless questions. Quite otherwise, it is, however, with questions concerning the questions concerning the immeasurably small. Knowledge of the causal connection of the phenomenon is based essentially upon the precision with which we follow them down to the infinitely small. The progress of recent centuries in knowledge of the mechanism of nature has come about almost solely by the exactness of the syntheses rendered possible by the invention of analysis of the infinite and by the simple fundamental concepts devised by Archimedes, Galileo, and Newton, and effectively employed by modern physics. In the natural sciences, however, where simple fundamental concepts are still lacking for such syntheses, one pursues phenomena into the spatially small, and in order to perceive causal connections, just as far as the microscope permits. Questions concerning spatial relations of measure in the indefinitely small are therefore not useless. If one premise that bodies exist independently of position, then the measure of curvature is everywhere constant. Then, from astronomical measurements, it follows that it cannot differ from zero. At any rate, its reciprocal value would have to be a surface in comparison with which the region accessible to our telescopes would vanish. If, however, bodies have no such non-dependence upon position, then one cannot conclude to relations of measure in the indefinitely small from those in the large. In that case, the curvature can have at every point arbitrary values in 3 directions, provided only the total curvature of every metric portion of space be not appreciably different from zero. Even greater complications may arise in case the line element is not representable, as has been premised by the square root of a differential expression of the second degree. Now, however, the empirical notions on which spatial measurements are based appear to lose their validity when applied to the indefinitely small, namely the concept of a fixed body and that of a light ray. Accordingly, it is entirely conceivable that in the indefinitely small, the spatial relations of size are not in accord with the postulates of geometry, and one would indeed be forced to this assumption as soon as it would permit a simpler explanation of the phenomena. The question of the validity of the postulates of geometry in the indefinitely small is involved in the question concerning the ultimate basis of relations of size in space. In connection with this question, which may well be assigned to the philosophy of space, the above remark is applicable, namely that while in a discrete manifold, the principle of metric relations is implicit in the notion of this manifold, it must come from somewhere else in the case of a continuous manifold. Either then the actual things forming the groundwork of space must constitute a discrete manifold, or else the basis of metric relations must be sought for outside that actuality in coagulating forces that operate upon it. Decision upon these questions can be found only by starting from the structure of phenomena that has been approved in experience hitherto, for which Newton laid the foundation, and by modifying this structure gradually under the compulsion of facts which it cannot explain. Such investigations as start out, like this present one, from general notions, can promote only the purpose that this task shall not be hindered by too restricted conceptions, and that progress in perceiving the connection of things shall not be obstructed by the prejudices of tradition. This path leads out into the domain of another science, into the realm of physics, into which the nature of this present occasion forbids us to penetrate.
So that, there's obviously a lot in there.
He mentioned a bunch of physical things, though. He talks about the astronomical measurements proving that we don't have a spherical universe.
Mm-hmm. He brought up some physical things.
Yeah.
Yeah, there's a lot there. So what he brought up as examples of things. So now we're applying things to space, applying these general concepts of what is the shape of space, and also considering, well, what does it mean in the infinitely large and in the infinitely small? Can we bring our observations and conclusions from the normal macro scale, can we bring it down and bring it out? Now, yeah, he gave two examples there of things that appear to lose their validity in the indefinitely small. And think about this, is really fun, these two examples he gives, that of a fixed body and that of a light ray. So for a fixed body, think about how material substances, what happens when you start getting really, really, really small? Do they still seem the same anymore? This was before Mendeleev, but this is certainly not before people considered atoms as a hypothesis. So there's definitely a feeling that something very different already, something different is going on down there. You don't put, if you just have hydrogen and oxygen gas, the gases themselves don't seem to suggest anything about a 2-to-1 ratio making water. But based, Lavoisier, 70, 80, basically 100 years before this, with Lavoisier's predecessors, there's already this sense that things combined in simple proportions. It's already forcing thoughts about chemistry. Anyway, I think that's something that he had in his mind on that. As far as the light ray goes, this was in the era of, we had Ampere, Riemann himself was working with Weber, following up what Gauss had done. So, on electromagnetism. And it was also very clear that something very different occurred with light in the very small. And based on diffraction and other experiments, it was known that light had characteristic wavelengths. So if light, which has, one character on the general scale, is acting like a wave once you get down very small, he knows something is different there. Our thoughts about space and physical processes that we use here, for how things operate, might not apply once we get way down there. So And then also, what is he saying about the shape of space? That, let me say one more thing. In the third to last paragraph, he says that, I'll just read it again. It's not like, you hear this once and it made perfect sense anyway. So let me read this third to last paragraph again. The question of the validity of the postulates of geometry in the indefinitely small is involved in the question concerning the ultimate basis of relations of size in space. In connection with this question, which may well be assigned to the philosophy of space, the above remark is applicable. Namely, that while in a discrete manifold, the principle of metric relations is implicit in the notion of the manifold, it must come from somewhere else in the case of a continuous manifold. Let's make sure we get that. He's saying that in a discrete manifold, the principle of metric relations, the basis of making measurements, is implicit in your idea of the manifold already. Why is that? You're counting discrete things. It means you must have some idea of what the things are if you're counting that kind of discrete.
The metric relations are part of a system that's inherent to it, like a key on a keyboard.
Yeah, a key on a keyboard, right.
It's not just a key, but it's in the context of a keyboard. So
if you say, what note are you playing, you have an idea of like what notes are already. Right. If you said, what frequency are you playing, then it's like, that's a little bit different. So in a discrete manifold, and even saying what the manifold is, you're already, just try to think of a discrete manifold where you're not basically already saying something about how you would describe what's in it. You think, so okay, so if it's discrete, the concept of measurement is already in the concept of the manifold. If it must come from somewhere else in the case of a continuous manifold. So the basis of measure, you make the measurements within a continuous manifold, but the basis of it doesn't lie in it. So he says either then the actual things forming the groundwork of space must constitute a discrete manifold, or else the basis of metric relations must be sought for outside that actuality, outside that space, in colligating, binding together forces that operate upon it. That's almost the same as the last sentence. So either space is discrete, in which case if we were to discover that space is discrete, we would only do it by understanding what that nature of that discrete manifold is. We have to know what's making everything happen to even say what it is, to say what that discrete manifold is. If it is continuous, the only basis that we'd have for understanding why the metrics are the way that they are lies outside the space that we're, outside of the relations in space, and it's in what are the physical principles, what are the colligating forces, the binding together powers that operate upon it, that make things happen. A decision upon these questions, he says, can be found only by starting from the structure of phenomena that has been approved in experience hitherto, for which Newton laid the foundation, and by modifying this structure gradually under the compulsion of facts which it cannot explain. Just think of Einstein here, right? Such investigations as start out like the present one from general notions can promote only the purpose that this task be not hindered by too restricted conceptions, and that progress in perceiving the connection of things shall not be obstructed by the prejudices of tradition. They're saying in this paper, we can loosen things up. We're not going to come to any conclusions today, though. And he says, this path leads into the domain of another science, into the realm of physics, into which the nature of the present occasion forbids us to penetrate. So,
is that his answer to the sentence, the final sentence of the third to last paragraph?
About the colligating forces that operate upon it?
Yeah.
Yeah.
So he's saying it's not the space is discrete. physics that we would be able to answer these things.
That's how we're going to answer it. I mean, maybe we'll find it's discrete. If it's continuous, the only basis for the metric relations would be coming from physics. So, like, let me take what Einstein did. So here's the important thing about, and let me respond also to, there were some comments that came in on the YouTube. I wasn't watching the YouTube channel, so Anthony, I didn't see your comments until just now about Euclid and about logic. So sorry I didn't respond to them earlier when they first came up. What you said here. The so in terms of Euclid, and what's wrong with Euclid? Is it that he said there was a parallel postulate? Is it that he said space was flat? I mean, that's wrong. What else is wrong with what he did? I mean, for one thing, synthetic geometry, and this is something I realized in some of the comments on the habilitation on the video, the other video on the habilitation dissertation. People got really upset about attacking Euclid, like really upset, which is kind of funny because it's like, who even knows who Euclid? Like, there's almost nothing known about his life, so he seems like a hard person to get attached to. What you get attached to about it is that he took, because it's not like people didn't know anything before Euclid. It's not like he invented the ruler or invented the compass, where there's never a square before Euclid, or people didn't know things like whether triangles were similar, or whether this angle is twice another one, or how to do constructions. Basically, he pulled together things that people had figured out and had standards of rigor and proof for already, of knowledge, and put everything into an axiomatic system in which any new thoughts in geometry would have to be subject to those axioms. So he took what could have been a developing physical geometry and did exactly what Hilbert and Russell were trying to do with math in 1900. I mean, the parallel is really direct. So is it just the parallel thing with Euclid? No. It's the replacement of logic for creativity. And to respond to your other comment, Anthony, about logic has been used in computers and everything, yeah, logical circuits are definitely used in computers, and it's true. The problem with it is not the use of logic circuits. The trouble is that what happened in 1900 wasn't a program for Hilbert to say, let's build computers based on logic to automate machinery. It was that this had, especially what Russell was doing, was to turn science into mathematics and into logic. So that's the problem with it. Science isn't logical. And if we were to try to axiomatize everything, there's really no more. There's no more knowledge that'll ever be made. There's no more discoveries to make. You kill creativity when you say that everything is going to be logical from now on, and that we're going to derive things from what we already know, because what we already know can't possibly encompass all possible true things about the whole universe. So. What do you guys think about this? About the paper, the conclusion? What are you thinking?
So I think what you just said about logic. I mean, you look at the second to the last sentence in the paper. Is to the point of what you were just talking about. That these researches, like the investigation we've just made, are useful in preventing this work. This work meaning, figuring out what are these coagulating binding forces going into the infinitesimal. This work in physics. Which is what he's aiming at there. That this investigation we've just made can be useful in preventing this work from being hampered by too narrow views and being checked by traditional prejudices, which is logic, which is the logic that you were just, the mathematical approach, the logical approach, are these narrow views and traditional prejudices. And that's exactly what has to be broken if you're going to do real science.
Right. Yeah, very, very good point. Right, you identify axioms, because if you're not aware of them, it's very hard to know that you're being subjected to axioms in your thinking. They're not always explicit either. in terms of your, like, you're not always just, if you try to be self-conscious, you can't just like magically know all the things that shape how you think. That takes work. If you could know all of that, then there'd be, I think every psychoanalyst would be out of business. There'd be no more psychologists. Oh, I know why I'm responding that way, because last week she, didn't refill the coffee pot. Now I'm pissed, and that's why I said that her idea was a bad one about the way we should do that. Right? Even on simple things like that, people are unaware. There's a couple things that also came in on the other means here. It seems that the change from the continuous violin to the fretted guitar presupposes the discovery first of the harmonies that would order the space. Well, that's interesting. I guess that's about, about space. Like, if we were to somehow discover that space was discrete, or like, to lay out a discrete manifold, you have to have some idea of what's actually making it first. You have to have a hypothesis for it first. They don't just come from measure. They come from an idea of what the thing is and how it acts that you are then going to measure. So, if you say how many, that's a silly one. Oh. And then another, let me find out which email account this is in here. Okay, here's another one that came in. It says, what made ideas like that of Riemann's, Vernadsky's, etc. not popularly known to people? And another question, pretty elementary, not specifically on what was just discussed. I remember from my college mathematics class that there's just Euclidean and non-Euclidean. But then LaRouche, in his numerous works, said that Gauss, Riemann, and the like aren't non-Euclidean, but anti-Euclidean. Could you address that, please? Great question. On the second part of it, about non-Euclidean versus anti-Euclidean, because this is a big distinction. Some of the people, if you look up non-Euclidean geometry or anti-Euclidean geometry, you're undoubtedly going to hear about Bolyai and Lobachevsky, who were people who were, I think both of them were trying to prove the parallel postulate, trying to prove, the flatness of space, and then realizing that it was impossible, said, well, maybe it isn't true. Let me replace this with a different idea. So both finding out what you could do with geometry without assuming parallel postulate, and then putting in alternative postulates. So, for example, a constantly curved, positively curved space, like for what a sphere would be to a surface if space were like that, and then you can work out what would the geometry be, or a constantly curved negative surface, like Beltrami. Other people have done work on this, and I think it was Lobachevsky, right, who did the astronomy work? Was it Boy? Do you remember which one? I forget. I get the two confused now. I think it was Lobachevsky, if I had to guess. One of them had actually proposed how to use astronomical measurements to try to determine the shape of space. So that's another thing Riemann's responding to here, about like if it's a constant curvature, what would astronomy tell us? I think he might be responding to what Lobachevsky, or maybe it was Bolyai, had done, where by using the two opposite parts of the Earth in its orbit, and then looking at a star, and then making that triangle, I think is what he had done. Tried to look at what the angles were in that to figure out if you could figure out the shape of space, if there's a curvature. And it was he didn't measure, as far as he could measure, it was flat. So that's maybe what Riemann might be referring to there. But what these guys what they had still done was they were still Euclidean, they were non-Euclidean as opposed to anti-Euclidean in respect to taking what Euclid had done and adjusting one of the postulates and then saying, let's see if it's right. In other words, they still had a mathematical basis for geometry. It was a different one. It wasn't Euclid's, but it was still geometrical geometry. And you say, is it right? And there was a parameter, the curvature, to try to determine experimentally. But, compare that to the huge leaps that Riemann's making, where, I mean, this is kind of amazing in these latter two sections here, where, with the quantum and general relativity, it seems you might take it for granted, because maybe you've seen a video about a bowling ball in a waterbed or something about general relativity. But Riemann's saying maybe space has got different measures of curvature everywhere. Maybe it's not constant at all. Maybe it's very different in the small. Maybe even if it seems like it's flat on the normal scale, it's got all sorts of complexity down in the infinitesimally small. We just don't know right now. And the only way we're going to find that out is by making the basis be in physics. That's anti-Euclidean. That's taking the whole thing that Euclid's built up from starting from axioms that are geometric, and instead saying the basis of geometry, the basis of metric relations, the basis of space, the basis of the relationships in space, that all of that, the basis of those metric relationships lies outside of space altogether. It's in the physics department, not the math department. So that is an enormous gulf between what Riemann had done and what Gauss probably already thought but never said, because that's what he did, compared to the work of Bolyai and Lobachevsky, who are definitely non-Euclidean, compared to Riemann being anti-Euclidean. I don't know.
Like Copernicus being non-Ptolemaic.
Oh yeah, right. Was Copernicus non-Ptolemaic or anti-Ptolemaic? Right. He was non. That's a good analogy. As far as how the reception of those thinkers during their lives, you know, I don't think Vernadsky was a big secret during his life. I mean, he was a very top person in Russian science who was hardly a secret name. I mean, maybe a lot of his work hasn't been translated, but it's not like he's a mystery in Russia. As far as Riemann, I really don't know what contemporaries knew of him. I mean, he was very famous. So do people today know about the Habilitation Dissertation and the importance of all of this? No. But people also don't know anything about Mendeleev. They don't know anything about Lavoisier. They don't know anything about the Pythagoreans. They don't know anything about Kepler. So, I mean, it's not about Riemann in particular. There's just a complete, I mean, there's a terrible educational system that's not based on remaking discoveries so that you own them, but instead of learning how to pass tests. Apparently, someone was telling me that even kindergarteners are being taught, some of their first lessons are how to take tests, like how to fill in bubbles so that the machine can grade their tests. And, you know, instead of having numbers for the questions, they say, like, in the thing with the pizza, you know, circle the thing, the letter, circle the shape that is what you put on your foot. It's like a shoe or something. Like teaching kindergartners to take bubble tests. Anyway, so, you know, just this whole educational approach that LaRouche is really insisting on, that if you're going to be a competent scientist, economist, if you're going to know how to make new discoveries, you actually have to study discoveries, not conclusions. And that's not what school's based on. It's studying conclusions, which not to say that they're all wrong, but you don't know if they're right or not because you didn't study that part. You studied the conclusions so you could do your answers correctly to get a good grade in the test. And unless you're lucky and have some lab component to it, you don't even know if it's true or not. You have no idea. So, so to answer your question, I think that, you know, those two in particular should be better known, but so should Kepler, for example. So should Kuza. So should people should be more familiar with Brunelleschi. I mean, there's a lot of work to do. People should be more familiar with LaRouche right now, huh? So, yeah. Okay. Any other thoughts?
Hey, Jason, you kind of started touching on this just now, but our group here in San Francisco, we missed the first few minutes. We had some audio issues. But if you could try to put this in a context, you know, here we are, we've got a campaign meeting, at least in San Francisco. We're a week away from a primary, and we're here working on this. You know, maybe you could help us to put this in of, you know, the impeaching Obama, bankrupting Wall Street, developing fusion,
right,
stopping Cold War, right, you know.
Right. Well, Riemann would certainly have impeached Obama. No, I'm just kidding. No, look, I mean, that's a very good question. You know, it often seems that, you know, things like this, you know, they're not directly related to, you know, does this, you know, tell you exactly, you know, do we take Riemann's geometry and apply it to, you know, where we should set up tables tomorrow based on the curvature of San Francisco or something? No. But the point of this is to get a sense of, you know, what is the human species, what is economy, what is science, because that's the full context of it. You know, we're making a renaissance. Like we've got a lot of political work that we do. We have important elections, you know, this week and then next week. So these things are obviously crucially important. the thing is also, what is it that we are trying to accomplish? What kind of citizenry are we trying to create? What's our real long-term goal? So, what are we trying to promote when we organize around the things that we organize around? What kind of people are we trying to create our context to become? So, obviously we live in an immediate political situation. I mean, obviously the threat of war is severe. The economy is collapsing very rapidly, heading towards Balin very soon, which puts sets the fuse on the drive for war from the British. But I suppose the simple thing is it's part of what's our alternative policy. So just as we have a policy for fusion, we need to develop fusion power. As this great article by Megan Beats about the suppression of fusion indicates, we would have had fusion power by now. We were on track. We were making so many breakthroughs in the 50s, 60s, 70s, and then it was just killed. And we don't have it today, although we should. And that was done intentionally to prevent the human species from developing. And science is the area most targeted for political control. I mean, if you're going to run an empire, you obviously have to keep people in line physically to some degree. You also have to, get them putting on their own shackles. You have to, so that comes in culture, for example. If you've got a culture that's based around pleasure and stupidity and, songs about really boring things that last for 4 minutes, and even during that they repeat something 3 times so they couldn't come up with 4 minutes worth of music. I mean, is it that hard? That's part of preventing people from thinking in a big way and taking on the task of being leaders. It shapes their self-conception. And then science is like, boom, that's like right there, the crucial thing. Because that is what shapes how people think that new thoughts are supposed to be made. So, when Lynn is saying that this 1900 shift was crucial for being a cause for what's now becoming more and more apparent as just the collapse of the transatlantic part of the world. The collapse of Europe, the collapse of the U.S., collapse of the Americas. The reason for it is it's a very deep one. And if you kill and destroy the creative potential of people, the concept of creativity in culture and in science, they're really not a threat to an empire, are they? Because they've got nothing better to fight for, except maybe they want more of the good stuff. But if you're fighting for a concept of the human species and the beauty and the dignity of what the human species could represent, it's important to immerse yourself and develop an understanding of culture, of science, of where we need to go. I mean, really, to be an economist, if we're, LaRouche won't be alive forever. If we're to provide the quality of leadership that he's been providing amazingly tirelessly for decades, we gotta know some of these things that he attributes his successful thinking to. So I think that's what I'd say about that.
Plus, there's no amount of politics. There's not even the savviest politician can save a world from crisis unless you're developing the minds of people.
Yeah.
Could you come back to your point about the hypothesis of the higher hypothesis?
The hypothesis of the higher hypothesis. Right, yeah, that's what we started with. So let me read that quote from Lynn again, and let's see if in context, see what we think about it again. So this is on page, I think, 90 or 91 in his economics textbook. LaRouche wrote, Riemann's 1854 Habilitation Dissertation on the hypotheses which underlie geometry is a hypothesis governing the formation of higher hypotheses for synthetic geometry, and is therefore an explicit statement on the subject of perfecting the hypothesis of the higher hypothesis. And then I meant to write the rest of the quote, but I didn't, and I didn't bring my printout. But then he says that all of his major breakthroughs were made on the basis of this work of Riemann's, along with, although he doesn't talk about it much anymore, the transfinite orderings of contour. But Riemann comes first, for sure. I mean, calls it the LaRouche-Riemann economics method. And when he when he's explained that in his papers, like on LaRouche's discovery, he describes his own thought about how to have an understanding of development itself in an economy. And this wasn't the only Riemann paper as far as LaRouche Riemann goes, but like take this whole concept and apply it to economics, for example. You think about monetarism as like a geometric space, and then think about physical economy as a Riemannian, anti-Euclidean, anti-monetarist space. So you've got the monetarist space of the economy, or even the physical existence space of the economy. You got things that are being produced, you got factories, you got bridges over here, railroads over there, you got a sewer pump over here, you got all these things. You got money flows all over the place, you got a whole lot of money flows in Wall Street and London. And then you say, well, what is it? What's the basis of what are the colligating forces that operate upon the economy that form the basis of its metric relations? So yeah, I think this is a very direct reference analogy to it, direct application, is that people try to, like in chapter 7 in So You Wish, which we just talked about last week. Lynn says that the problem with economics, with economists, is that basically they try to make everything in terms of the magic of the marketplace and price theory, the money measures, and secondly, it's just PR to promote usury and empire in the guise of an academic theory, when really it's just an excuse for empire, and people make it up as though it's some economic thought. And he says that if you throw that away, understanding money is pretty simple. And then he goes and he puts money in the context of a credit system, and that the basis for prices, the basis for the money that we use, the basis for economy, the measurements, they can't be in GDP, they can't be in money terms. The basis of economic value is the transmission of negentropy. The basis of economic value is the development of new discoveries, is the development of implementing discoveries, of creating a culture that fosters creativity. So, that's economic value. And does that project down onto, are we going to use money? Is LaRouche envisioning a world where there's no money? No, he's not. I mean, that's, what are you going to barter? So, you use it, but you don't run your economy based on it. Are there metric relations in space? Yes. Do we measure things in space? Sure. Is the basis of understanding those space? No, it's physics, right? Take what Einstein did with general relativity. The basis of those metric relations of the curved spacetime of general relativity, it's not Einstein didn't have some idea about just space. He had an idea about physical spacetime, about gravitation. Physics is a colligating force that's that's forming the basis of the metric relations of curved general relativity spacetime. So, same thing with economics. Physical economy, that provides a legitimate basis for metric relations of money, for example.
Hey, Jason?
Yes.
Yeah, one example in physics of what Riemann is getting at the end is the photoelectric effect. Where what appears to be a continuous wave is actually causing a discrete output or discrete effect.
Right. Yeah, absolutely. And that's one where, you'd say these two choices that he's got, saying, well, either the actual things forming the groundwork are a discrete manifold, in which case, if they are, we've already got a concept of metric relations in them, or it's continuous. And as the world of the quantum shows us, I guess I was talking about the colligating forces that are operating on the continuous manifold, but also we got Planck, we got the quantum. So I think about Einstein and Planck did exactly what Riemann's talking about in this paper. Planck's looking at the basis of metric relations in a concept of discreteness to underlies the quantum, and Einstein is giving a specific hypothesis about the shape of space based on a physical principle. So, yeah, this is an awesome paper. Okay. Well, hold on. A couple more things came on Google+. Let's see. Otherwise, I was going to say it's 10:30, which is a nice even time, so maybe that's a good time to. Let's see here. Here it is. You have not addressed my point that the fifth postulate is a postulate, not an axiom. I mean, Euclid still went with it. It's not like he said this is a possible space. This is what he built his whole thing on. I disagree that Euclid's axiomatizations... No, I mean, Anthony, if I had suggested, read... I've got a paper on this whole thing, Gödel, Russell, Riemann, and Euclid. It's in the video description. I think that take a look at that, you know, right back again with your thoughts on it. But take a look at that paper. It goes through that train of thought pretty thoroughly. Okay, anything else from our live internet audience? Oh, a text came in too. Oh, no, it's about something else. Okay.
Yep.
Well, I think that'll wrap it up. Thanks for joining. Good night.
Thanks, bye.